Good evening, everyone. Uh, in Unit 2, we are in last class. We had discussed about non-ideal flow, the characteristics of a non-ideal flow, which parameters makes a sense, will differentiate a real reactor from an ideal reactor. What are the non-ideal characteristics in a real vessel? We have seen last class. There are four important parameters that we have seen in the last class. One is non-idealities in a real vessel, state of aggregation, macrofluid, microfluid, and also we have discussed about early mixing in a reactor and also late mixing in a reactor. Finally, our objective is at the end of this unit, non-ideal flow, we are in a position to calculate by obtaining some different models in order to uh, find out the conversions in a non-ideal reactors. Finally, our objective is to find out the conversions in a non-ideal reactors called as a real vessel. Then, for which there is a very important parameter useful to find out the conversions, that is residence time distribution. Residence time distribution, RTD. It is also called as a exit age distribution. It is a real vessel. We are conducting experiments over a real vessel. That's why there is an irregular shape I have drawn here. We have an inlet of the reactants. There is a probe is introduced at the exit of the reactor, which measures the concentration of the outlet of the reactant substance by using certain parameters like refractive index, thermal conductivity, volumetric titrations, etc. Let us consider a real reactor or real vessel into which packets, globules of molecule, that means either macrofluid or microfluid. Reactant molecules like macrofluid enters. Each packet of molecules will take various parts in the reactor vessel and comes out of the reactor. These reactants will take less span of the time. These reactants is a longest path here will take more amount of time. Each packet of molecules will be a timer equipped with a timer by which the time spent by the packet of molecules will be estimated. Equipped with a timer by which we can the molecule time spent by each and every molecule will be known. The concentrations of each packet of molecule at the exit, time spent by each packet of the molecules at the exit, can be calculated by the probe. This is a probe which is placed at the exit of the reactor vessel. Placed at the exit of the reactor vessel. This is the probe. Concentrations can be measured by using the probe. Uh, the time spent by the packet of molecules in the reactor vessel are called as residence times or excitation times. There are different times are there. The time spent, this is the time spent by each and every molecule, the packets of the molecules plotted on x-axis. These times are also known as excitation times or residence times. And when y-axis, the concentrations measured from the probe are drawn on y-axis. This is C versus T. This curve is called as a C curve. A plot is drawn between concentration of the molecules versus time or also number of molecules versus time. It looks like a distribution function called as excitation distribution function, denoted with E of t. Excitation distribution, it's a distribution like a marks obtained by the students in a classroom. It looks like a distribution. If it is a straight line, marks obtained by the straight line it's a non-ideal thing. It means each and every student will have the same marks. It's a non-ideal. It should be distribution of the marks, the number of the students versus marks. If I plot like these many number of the students got minimum marks, these are number of students also, like less number of the students and also maximum number of the students also got or like name of the students also got less number of the marks. These students got more number of the marks. Likewise, uh, the concentration of the molecules, low concentration of the molecules here comes out here also, where they are very late, like old molecules, where some of the young molecules will comes out by spending very less span of the time in the reactor. This is the shape of the C versus T curve called as a C curve. The C curve is mainly used to find out the E curve. There are three different curves we are going to discuss in the later chapters. One is a C curve, another one is E curve, another one is F curve. E curve should come obtained from the C curve, F curve is obtained from the E curve. But how to estimate this E of t? How to estimate this E of t called as the exit age distribution or residence time using a stimulus response. That technique is called as a stimulus response technique. In order to estimate this E of t, we are using a tracer. A tracer is a small amount of fluid used to estimate exit age distribution by using stimulus response technique. What exactly a tracer? Tracer is a small amount of the fluid having the properties like flowing fluid, reactant fluid, heat. What are the properties that reactant fluid having, like density, viscosity, surface tension? All these properties like same like the reactant tracer should have the same properties. And this tracer should be immiscible with the reactant fluid, having a low viscosity, non-toxic, should be non-corrosive, and also easily available, and low cost also, and also easily detectable. These are the main properties of the tracer. We will try to select this tracer and we'll try to introduce the tracer because how the reactant fluid flows the same way, same pattern, same time. It will take the same time, residence time like a flowing fluid. Like that, we will take a tracer, like a dupe. Dupe for a hero in a cinema, like we will have a dupe that is called as a tracer in the reactor. The tracer is easily detectable, like it is having some different color. I think we can easily, from the titrations, we can easily know the concentrations at the exit of the reactor. We are conducting, we are having one RTD experiment in our laboratory also, chemical reaction engineering laboratory. Also, we are conducting the experiments also, RTD in a flood flow reactor. Very interestingly, we are going to observe what exactly the tracer and what are the outlet concentrations of the tracer, what we are using at different time intervals. It's a beautiful experiment. I think you can easily understand what this experiment in our laboratory also. When coming to the lab, after listening this classroom, please come to the lab and complete the experiment. I can easily understand what tracer and what RTD experiment is. And yes, this is what the pulse input, tracer pulse. Pulse is looks like this. It's like a Dirac delta function. We'll discuss later. It is like immediately, for example, 5 ml of tracer we are introducing. In our laboratory, we are using acetic acid as a tracer. 5 ml we are taking. 5 ml we are introducing at at once only. That means like within few seconds we are introducing the entire tracer of 5 ml into the reactor. That's why the height of my function should be infinity, width should be very less, area under the curve should be infinity. 100% of the tracer is introduced in the reactor. And we have a concentrations of C naught is the concentration, M is the weight of the tracer, mu is the volumetric flow rate. Outlets are the same volumetric flow rate, outlet concentration changes, the total mass will comes out like this. This is the concentration versus time. This is C curve, how it will looks like at the exit of the reactor. It's a real vessel. Let us consider a pulse input of tracer of initial mass concentration C naught having unit of kg per meter cube with mass m kg with volumetric flow rate mu meter cube per second introduced in a real vessel in order to estimate exit age distribution function. E of t unit is minute inverse. But what about E of t delta t? This is minute inverse. E of t unit is minute inverse. Delta t is minute. This is a dimensionless. E of t delta t is a dimensionless. E of t delta t signifies about the fraction of reactant molecules will spend or comes out from the reactor vessel in between T and T plus delta T. Let us try to see like this. 5 ml of acetic acid we have introduced in the reactor. We have conducting the experiment. We have started 10 o'clock. Experiment is started 10 o'clock. It's like 10 o'clock I have started. At 10:30 I'm going to finish my experiment. That means 30 minutes time is required. Assuming that 30 minutes time is taking by my acetic acid of 5 ml introduced in the reactor, it comes out all the amount. In order to comes out all the amount, it will take 30 minutes. That is what my basic understanding. In 30 minutes, all my 5 ml is coming out from my reactor. What this T and T plus E of T delta T indicates that the fraction of the molecules, for example, I want to know about what are the total amount of fraction of the molecule comes out in between 10-15 to 10-20, 10-15 to 10-20. Within the 5 minutes, what is the amount of the fraction of the material, reactant material comes out from the reactor, it will give from the area under the curve. This is called as a E of T delta T. This is the fraction, area under the curve in between 10-15 to 10-20 minutes. In 10 to 10:30, the entire amount of total amount of material comes out from my reactor, but within this 15 minutes, this is your integral of 10 to 15, 10, 20, 15 to 10, 20, this nature of this curve. That is what E of T delta T. Let us try to have a material balance for the tracer. That delta M is the mass of the reactant material comes out from the reactor in between T and T plus delta T. Delta M can be estimated by mu unit is meter cube per second, C kg per meter cube, and delta T. Delta M is very highly difficult to find out, but I know I can find out mu by rotameter or venturi or orifice, volumetric flow rate. Concentration can be known by refractometer method. Time also be known. That's why this delta M is mu C delta T. But total M is the total mass, can be estimated by integral 0 to infinity, 0 time to infinity time, the amount of total amount of material comes out. That can be written as 0 to infinity mu C dt. Mu C dt. Thus, the fraction of material comes out from the reactor in between T and T plus delta T is fraction. Can I write fraction as delta M by M, that is E of T dt. E of T dt signifies the same information. Delta M by M also signifies about the same information. If I have nu C delta T by integral 0 to infinity nu C delta T, as nu is a constant, same, cancel, C delta T by integral 0 to infinity C dt. This delta T is cancelled. E of T can be calculated as, very very important, C by integral of 0 to infinity C dt. This is in the problem, examinations problem, definitely problem will ask. We need asking on based on construction of E curve. E curve can be constructed by finding out the different C values and divided with the area under the curve between C and T. Area under the curve of C and T. E of T as C by integral 0 to infinity C dt. This can also be written as C by integral, can also be written as sigma C into dt. If delta T is same, if I have a data like 1, 2, 3, 4, 5 time intervals, delta T is 1. If delta T is same for the entire data, I can make it outside of this sigma, then C by delta T into sigma C. From equation 1, we can write E of T as C by integral 0 to infinity E delta T, or C by area under the curve of C versus T. This area under the curve we can write it as